Okay, in this video we continue our discussion on incident matrix of a graph. So here we define what is called the reduced incident matrix of a graph, and we prove that the reduced incident matrix of a tree has rank n minus 1, where n is the number of vertices in that tree. Okay, so let me start by defining the reduced incident matrix. Okay, so suppose that we have a graph G, and G is a connected graph with n vertices and m edges. Okay, then in the previous video we saw how to define an incident matrix. Okay, and we saw that the order of the incident matrix is n by m. For example, if you consider this graph G, okay, and here this matrix, it corresponds to the incident matrix for this graph. And from the previous video we know that the rank of this matrix, so here we can see that this matrix is, so here we have 4 vertices and 5 edges, so the order of this matrix is 4 by 5, where 4 is the number of vertices and 5 is the number of edges. Okay, so from the previous video we know that the rank of this graph, and we can see that this graph is a connected one. Okay, and from that result we know the rank of this incident matrix is n minus 1, where n is the number of vertices. So here the number of vertices is 4, so the rank of this matrix is 3. Okay, so from the previous video we know the rank of this particular matrix is 3, and in general, okay, we can see that the rank of this incident matrix is n minus 1. Okay, so if we remove any one row from AG, the incident matrix of this graph G, the remaining n minus 1 by m submatrix is of rank n minus 1, since we are dealing with a connected graph. Okay, so in the previous video we proved the result that if G is a connected graph with n vertices, then the rank of the incident matrix is n minus 1. Okay, so that says if you remove one row, okay, we get a matrix, a submatrix of order n minus 1 by m, and the rank of that matrix is n minus 1. Okay, so that we can very easily verify from this particular matrix also. So if you take any row, suppose that if you take this row and if you remove that row from this matrix, okay, we can see that this submatrix, it has order, in this case 3 by 5, where 3 is nothing but n minus 1. Okay, and this submatrix, it has rank n minus 1. Okay, so we can see that that submatrix has rank n minus 1. Okay, such an n minus 1 by m matrix of the incident matrix is what is called a reduced incident matrix, and usually it is denoted by a sub f. For example, if you consider this graph, okay, and here we have this submatrix, and here this submatrix is what is called a reduced submatrix. Okay, so that says something like this: if you take any incident matrix of a connected graph with n vertices and m edges, and if you remove any row from that incident matrix, then we will get a submatrix of order n minus 1 by m, and the rank of that will be n minus 1, and such a submatrix of order n minus 1 by m is what is called a reduced incident matrix, and it is denoted by a sub f. Okay, for example, again you consider this particular graph, and if you remove this row, then we have a submatrix of rank in this case 3. Okay, and similarly you can also see that if you remove any row, okay, we will get a submatrix of order 3 by 5, and that is going to be of rank 3 in this case. Okay, and in this case this submatrix is called a reduced submatrix, and okay, for this I think we could represent this submatrix something like A sub f of G. So that is going to be this matrix. So that is how we define the reduced incident matrix of a connected graph. And here, okay, if you delete any row, then we get a reduced incident matrix. Okay, so the vertex corresponding to the deleted row in the reduced incident matrix is called the reference vertex. Okay, so for example, if you consider this example, so here you obtain this reduced not reduced submatrix, so reduced incident matrix. Okay, so here we deleted this row to get this reduced incident matrix. Okay, so that says, okay, for this matrix we deleted this row, and that row corresponds to this vertex E4. So here this E4 is what is called the reference vertex. Okay, so in this case the reference vertex could be a V1, V2, V3 or V4. So again we can see that if you delete the second row, okay, again we will get a submatrix, and that submatrix it is going to be another reduced incident matrix. Similarly, if you in that case the reference vertex will be V3. Similarly, if we delete the first row, okay, we will get a submatrix of order 3 by 5, and that is going to be another reduced incident matrix. And in that case, okay, I think if you delete the second row, then V2 it is going to be the reference vertex. Okay, so that is the definition of what is called a reduced incident matrix, and it is denoted by A sub F. Okay, so now to get a reduced incident matrix, we take an incident matrix of a connected graph and delete any row. Okay, and the resultant subgraph of order n minus 1 by m is what is called a reduced incident matrix. And since in the incident matrix every row corresponds to a vertex, and that deleted row, the label of the vertex corresponding to the deleted row is what is called the reference vertex. So I think the definition is clear, and now we are going to prove a statement related to the incident matrix of a tree. Okay, so this statement says the nature of the incident matrix of a tree, and the statement reads as follows: a connected graph G is a tree if and only if the reduced incident matrix of G is non-singular. Okay, so non-singular means that particular matrix is invertible. Okay, so let's go and prove this theorem. So here we can see that the statement is in if and only if form, so we have to prove both direction. Okay, this direction and the other way. So this direction reads as follows: if a connected graph G is a tree, then the reduced incident matrix of G is non-singular. And the other direction will be like, if the reduced incident matrix of a graph G is non-singular, that is invertible, then okay, that graph is a tree. By the way, that graph must be a connected one also. Okay, so let's go and prove both direction. So let's prove this direction. So we are going to prove that if G is a connected graph, okay, then the reduced incident matrix of G is non-singular. Okay, so we know that a tree with n vertices has n minus 1 edges. Okay, so that is by definition. A tree is nothing but a acyclic connected graph. Okay, and it is a connected one, and we know if a tree with n vertices has n minus 1 edge. Okay, so we proved these kind of theorems when we discussed about trees. So a tree with n vertices has n minus 1 edges and is also connected. Okay, so here we have this n vertices and n minus 1 edges. So if you look at the incident matrix, so if you so okay, so the incident matrix of that tree, okay, it has n rows, okay, where this n corresponds to number of vertices, and n minus 1 columns, because this n minus 1 corresponds to the number of edges. Okay, and since the graph is connected, the rank of this matrix, okay, so since the graph is connected, the rank of the incident matrix is n minus 1. Okay, so if you look at the reduced incident matrix, the order of the reduced incident matrix will be n minus 1 by n minus 1. So the reduced incident matrix will be a square matrix, and the rank of that matrix is n minus 1. And from linear algebra, we know that if you have a square matrix of having full rank, okay, so in this case we have a square matrix of order n minus 1 by n minus 1. Okay, and the rank is n minus 1, so it has a full rank, so that matrix is invertible. Okay, and that's what we are trying to prove here. Okay, and that's it. So let me complete the proof. Okay, so therefore the reduced incidence matrix is, okay, a square matrix of order n minus 1 by n minus 1. Okay, because here we are dealing with a connected graph with n vertices and n minus 1 edges. Okay, so the incident matrix has n rows and n minus 1 column, and the reduced incident matrix will have n minus 1 rows and n minus 1 columns. So the reduced incident matrix is obtained from the incident matrix by deleting one row, right? So therefore the reduced incident matrix is a square matrix of order n minus 1 by n minus 1, and this has rank, okay, with rank n minus 1. Okay, so this particular thing, the reduced incident matrix is a square matrix with full rank. Okay, so okay, reduced incident matrix square with rank n minus 1. So the reduced incidence matrix is invertible or non-singular. Okay, and that's what we want to prove for the direction. So we proved that okay, if a connected graph G is a tree, then the reduced incident matrix of G is non-singular or invertible. Okay, so that's the first part. So let's go and prove the other direction. So the direction says, okay, if the reduced incident matrix of a connected graph G is non-singular or invertible, okay, then G is a tree. Okay, so we are going to prove the contrapositive of that statement, and that says, okay, if a connected graph G is not a tree, okay, so something like with n vertices and n minus 1 edges is not a tree, okay, then the reduced incident matrix of that graph is singular. Okay, equivalent statement. Okay, so let's go and prove that. Okay, so for the other direction, okay, again it is going to be a very simple proof. So we can very easily say that a graph okay, G with n vertices and n minus 1 edges, okay, which is not a tree, is disconnected. Okay, so this is very easy to see anyway. So a graph G with n vertices and n minus 1 edges, which is not a tree, okay, it must be a disconnected graph. Okay, so that says if you look at the rank of the incident matrix, okay, of this graph G, okay, then it's a disconnected graph, and since the graph is disconnected, the rank of the incident matrix will be strictly less than n minus 1. Okay, so therefore the rank in the previous video, as a corollary for the statement, we proved that if the graph is disconnected and have k connected components, then the rank of that matrix will be n minus k, where n is the number of vertices in the graph, right? So in this case, the rank will be strictly less than n minus 1. Okay, so therefore the rank of the incident matrix of G is strictly less than n minus 1. Okay, and that says, so the rank of the incident matrix of G is less than n minus 1, so it will be like n minus 2 or n minus 3 or something like that. And that says if you look at the reduced incident matrix, okay, it has rank less than n minus 1. Okay, so the rank, the reduced incident, okay, rank of the reduced incidence matrix is less than n minus 1. Okay, so here we started with a graph with n vertices and n minus 1 edges. So that says the incident matrix is of order n by n minus 1. And since the graph is disconnected, the rank is less than n minus 1. And here the order of the reduced incident matrix will be like n minus 1 by n minus 1, and the rank of the reduced incident matrix will also be less than n minus 1. So it is not full rank. Okay, so the rank of the reduced incident matrix is less than n minus 1, and hence the reduced incident matrix is not invertible or singular. Okay, and that's what we are trying to prove here, right? And that says if the reduced incident matrix of a connected graph G is non-singular, okay, then the graph G is connected. Okay, so we are able to prove both directions here. Okay, and that's the proof. So hence we have the result. Okay, hence the n minus 1 by n minus 1 reduced incident matrix of a graph non-singular, okay, if and only okay, that graph, okay, graph is a tree. Okay, exactly the same statement that we are trying to prove. Okay, so in this video we defined what is called the reduced incident matrix, okay, and we proved the nature of the incident matrix of a tree. So we proved a connected graph G is a tree if and only if the reduced incident matrix of G is non-singular.